Hello everyone, this lesson is going to be on acceleration and it kind of follows a previous lesson that I had on distance, displacement, speed and velocity. We'll start by taking a look at your data sheet here and the physics formula so we see what it is that we're taking a look at. So prior to this we already saw these first two equations here for speed and velocity, the equations or formulas, the variable symbols, the variable names, and the units, of course, that go along with them. And now we're going to be taking a look at this one kind of right in the middle here. So lowercase a for acceleration, arrow up above, which means it is a vector. There is a direction associated with it. And that's really because we do use velocity, and velocity itself is, of course, also a vector. So acceleration is equal to the change in, delta once again is the change in, that triangle delta, change in velocity. So here they've just expanded that a little bit, final velocity minus the initial velocity divided by the change in time. We'll see that that is equal to the acceleration. And then we do see here as well, it tells us, yes, A is for acceleration and the units meters per second squared. So that's what we're going to be using in this lesson here for our calculations. So what do we mean by acceleration? Well, we're talking about how fast an object is going, the speed or the velocity, and it's not the same. It is changing. So because the velocity is changing, we call the velocity non-uniform. So it can be going up and going down. It can be consistently going up, consistently going down. But if it's not the same, it is changing, and then it is non-uniform velocity. Kind of confusing though, as we can talk about uniform acceleration, even though we have a velocity that is changing over time. So with acceleration, kind of helps to think about, sort of real life and a vehicle. If you're sitting at an intersection at the stoplight, your speed, your velocity is 0 and your acceleration is 0. But then when the light changes to green, all of a sudden what's going to happen, if I make this kind of visual down here as well, I won't draw a car, but we'll say that we're heading toward the right here. So initially when the light changes to green, you're going to start off kind of slow, but then you go faster and faster and faster and faster and faster. And because you're going faster and faster and faster as time progresses, we say that you are, well, accelerating. And that's exactly what it means, is the object, the car, you, is traveling faster and faster with each time period that does pass. When you step on the accelerator at the green light, you have positive acceleration. You're going faster and faster. When you reach a red light and you slow down, you have negative acceleration, or also referred to as deceleration. So let's take a look at those variables again, the name for them, the units, and the equation from your data sheet. So on here, I wasn't able to put in the arrow up above. So I say here, italicized letters mean vectors, but I can write it with my pen. So there would be an arrow over here. There would be an arrow over here as well when we're talking about velocity and we're talking about acceleration. So yeah, lowercase a for an average acceleration is what we talk about in this course. Delta V, again, change in velocity, so it is the final minus the initial. And same with time, it is the change in time. Second time, final time minus the initial time. Units for acceleration, it is velocity divided by time. Units for velocity, meters per second, or speed. Units for time, seconds. So the overall units are meters per second squared. And as I have here, think of it this way. With each second that passes, your meters per second is changing. With each second that passes, your velocity is changing. And that is what acceleration is, whether it is positive or negative acceleration. So let's jump into some problems here, and then we'll take a look at a few graphs as well. So a bobsled traveling down a track, well, I guess we could maybe say there's a direction that's kind of going downhill and zigzagging around. Bobsled traveling down a track goes from rest. So initially it is 0 meters per second. And then the final is going to be 20 meters per second. So I'm just going to write this here. This is going to be our V1. This is going to be our V2. We don't necessarily have to show that calculation. I can just write that the change in velocity or speed is equal to 20 meters per second. Again, think about the units. We do want meters, we do want seconds, so that is all good at this point. Time, we're given our time. Time in seconds, change in time is equal to 4.5 seconds. Okay, grasp. Given information, we have required information. Well, we want to know the acceleration. That's what we're trying to find. We have the given, we have the required. A is the analysis, that is the equation. Acceleration is equal to the change in speed or velocity divided by the change in time. We've now taken care of that. Your solve is just plugging the numbers in. So change in velocity, 20 meters per second. Time, 4.5 seconds. The seconds do not cancel out here. You do end up with meters per second squared. And when you do take your 4.5, or sorry, your 20 and divide it by 4.5, you do end up with 4.4 to the correct number of sigdigs. Least precise number here is the 20. That trailing zero, it is significant, so we do have 2 sigdigs. And that's what we should have in our answer. Double check your units. Is that what we want for acceleration? Yes, it is. This is our answer, 4.4 meters per second. Second question that we have, car traveling at a constant acceleration. So we would also call this uniform acceleration. So the velocity is not uniform, it is changing, but the acceleration is constant. So 5 meters per second. So with each second that passes, it's going 5 meters per second faster. So again, how do you think about that? Initially, it's going 0. After 1 second, it's going 5 meters per second. After 10 seconds, it's going 10 meters per second. With each second that passes, it's going 5 meters per second faster. So how long, we're looking for a time, will it take to reach this velocity here? And notice that this is not in the units that we want, right? It is not in meters per second. We can't have meters per second or meters and seconds here and kilometers per hour for our other numbers. So we're going to have to make a change there, and we're going to make the change there right away as well for that. So we'll go ahead and write down what we have. So our acceleration, we do have that number, and that is equal to 5 meters per second squared. That's given information. Speed or velocity, we have 72 kilometers per hour. So I'll take you through how we go and do this conversion. So let's take a look at the kilometers first. We want to get rid of the kilometers. Kilometers is in the numerator, so we're going to multiply by something that has kilometers in the denominator so they cancel out. In 1 kilometer, we want to convert it into meters, right? In 1 kilometer, there are 1,000 meters. So kind of think about this. 72 times 1,000 is 72,000. 72,000 meters in a kilometer seems reasonable. So that is correct. Now we need to, we got rid of the kilometers, we've converted it into meters. Now we need to get rid of the hours. We want to cancel out hours. It's in the denominator. So now we put it in the numerator. In 1 hour, there are 3,600 seconds. Okay, so 60 seconds in a minute, 60 minutes in an hour. Multiply those together, and I get the 3,600 seconds per hour. That's where that came from. So what are we doing? 72 times 1,000, 72,000 divided by 3,600, and that works out to 20, nice even 20 meters per second. Are those the units that we want? Yes, because it is a speed or a velocity. What are we looking for? We're looking for a change in time. Okay, so now we have our given information, our required information, equation, acceleration is equal to the change in velocity divided by the change in time, but we are looking for the time. So we want to rearrange this equation, get it to the other side. So I've shown you various different ways to rearrange these equations. Let me show you this one this way. I'm just going to put this over 1. If I have time in the denominator to the right of the equal sign, if I move it to the other side, it ends up in the numerator. Acceleration is in the numerator to the left-hand side of the equal. If I move it to the other side, it ends up in the denominator. So all I'm really doing is I'm kind of flipping around the time and the acceleration. So change in time is then equal to acceleration. Oops, sorry, not acceleration. Just scrape that out. Change in velocity divided by the acceleration that is now in the denominator. Okay, velocity we have, acceleration we have. All we need to do is plug those in. 20 meters per second is what we have for velocity. Acceleration, we're told is 5 meters per second squared. So what actually goes ahead and cancels out with this one? Meters cancel out. One of the seconds does cancel out. And we end up with seconds in the end. 20 divided by 5 is 4, and it is 4 seconds. 1 sig dig up here, 1 sig dig is what we do want for our answer as well. So graphs, understanding motion graphs, really, really important. Time for any of these motion graphs, whether it's a position time graph, displacement time graph, velocity time graph, time is always on the x-axis, the horizontal axis, and we'll see a number of these graphs. We'll take a look at this as well. Velocity is the slope of a position time graph. If you have a position time graph, and if you calculate the slope, that does give you the velocity. We'll take a look at how you do that. Displacement is the area under the curve for a velocity time graph. Remember that work was the area under a force distance graph. Acceleration is the slope of a velocity time graph. And the change in velocity is the area under the acceleration time graph. So let's take a look at a few of these graphs here. This is really kind of nice. We kind of work across here horizontally. So all of the ones in this first column, they are, I'll just write it as position. They are the position time, because it's always time, on the x-axis, right? Time on the x here, time on the x here, time on the x here. On the y-axis, here x is for position. Here it's for velocity or speed, and here it's for acceleration. Okay, so all of these three, they go together. These three that are in the first row. This object is stationary. What does that mean? It's not moving. So it doesn't have us numbers, or doesn't give us numbers. It doesn't matter. We can put this as 1 and 2 here, and we can put this as 5, and we can put this as 10. It doesn't matter. We're just looking at the shape of these curves here. So what it does show is that if it's a stationary object, it's right here, maybe at the 7-meter position, and it's not moving. So as time goes on, it's staying at the 7-meter position. It is not moving. Well, if it's not moving, there's no velocity and there's no acceleration. The slope of the position time graph is velocity, but here there's no change in position. So if our delta x for position equals 0, then the slope is going to be 0. So that's why velocity is 0 and acceleration is 0, if you have a stationary object. Hopefully that makes perfect sense. Let's get the object moving. So here it says uniform motion, and here it's really talking about the velocity is consistent. It's the same, it's not changing. Our position time graph, what does it show? Well, as time goes on, the position is changing. Not only that, it's a straight line. So this tells us that it is uniform. After 1 second, it's gone 5 meters. After 2 seconds, it's gone 10 meters. After 3 seconds, it will have gone 15 meters. So it's a consistent change that we do see. It is moving, so there is a speed or there is a velocity. Now the slope. If we take the slope of this, slope is equal to the rise divided by the run. This here is the rise. This here is the run. Well, you'll notice that the rise is the position. Just to be consistent with what we've been doing in class, that's change in d, or displacement, and delta t is the run. So if we take the slope, the rise over run of the position time graph, that is distance over time, which is velocity. So now if we take a look at the velocity time graph, we can see that it's not zero. The object is moving. We do have movement that is taking place. Because it is uniform velocity, the velocity is the same. So yes, there is movement, but it's consistently going at the same speed or velocity. It's not accelerating. So the acceleration is still zero with this one. The last one here, now what we do have is acceleration. So the object is going faster and faster and faster all the time. Here it's going at a constant speed. If it's going faster and faster, what we're going to see is it curves up. Okay, so this is if it's going faster. If you had a curve that goes like this, it's slowing down. It's going slower. Okay, but we're taking a look at this one here where it's going faster and faster all the time. So now let's go to our velocity time graph. If it's going faster and faster all the time, well, its velocity or speed is increasing all the time. If it's increasing all the time, that is acceleration. So up here, we took the slope of the position time graph, and that gave us the velocity. If we take the slope of our velocity time graph, that gives us acceleration. Okay, so let's actually pick some numbers here. Let's take this time right here. Let's just say that this is 1 second and this is 2 seconds, and that this is 5 and this is 10. And we'll just say that this, to make it easy, is right at 10. So what is our rise? Rise is equal to the final number, 10, minus the initial number, 0. 10 minus 0 meters equals 10 meters. Our rise is 10 meters. How about our run? It's the final minus initial, which is 2 minus 0 equals 2 seconds. Okay, so we have 2 seconds. And we have a rise. Actually, this one is meters per second, of course, because it's speed or velocity. And meters per second. So slope is the rise divided by the run. Squeeze it in over here. Slope equals rise divided by run. Our rise was 10 meters per second. Our run was 2 seconds. That's equal to 5 meters per second squared. Meters per second squared, that's velocity. That's what this is right here. So we take the slope of the velocity time graph, and that's equal to acceleration. We take the slope of the position time graph, and that's the velocity. Just one more picture that we'll quickly take a look at here. We could spend a lot of time taking a look at this one, and you probably should. So what this shows us is similar information. The top graph is showing position, corresponding to the change in speed or velocity in the middle one, and then acceleration down below. So let's take a look at a couple of portions of this. So what did we see with the position time graph if it curves up? Well, that means it's accelerating, so the velocity is increasing all the time. So yeah, that's what we see. Velocity is increasing all the time. What does that mean in terms of acceleration? Yes, it's accelerating. We have a number for that. What happens with the next part? Well, now it flattens out. So it's not curving up, but it's actually straight here. Because it's straight, it's not speeding up, it's not slowing down, it's going at the same speed or velocity. And that's why this next segment here for the velocity time graph is horizontal. If it's not speeding up or slowing down, there's zero acceleration. So this is an object that speeds up, goes in one direction, and then it slows down, and then it stops right here, and it goes back. So when it curves down, it's slowing down. The velocity is decreasing, and because it's slowing down, we get a negative acceleration. Then when it stops, it goes back in the same direction. Okay, so again, this is position. This is where it started. Now it's going back in the direction. It doesn't reach where it started, but it's going back in the same direction. So this is an object that starts here, moves in this direction, and then it goes back in the opposite direction. Initially, it's accelerating, then it's staying at the same speed, then it's decelerating, then it's accelerating, but it's a negative acceleration, and then it's decelerating at the end again. So I mentioned right at the peak here, it stops, and that's when it starts to go back. Okay, so right here on my picture, that is where it stops. So if it stops, what's the velocity? Well, at that point it's zero. And it's going to immediately start to go back in the opposite direction. So that again is a negative acceleration. That's why it's down below the zero here. And then finally, when it slows down, that is a negative acceleration, but it's going in the opposite direction. So it actually appears up above the zero line here. So most definitely you should be able to take a look at and interpret these graphs and the previous ones as well, and be prepared to do some calculations for the slope and answer questions related to these graphs.